Hello. So we continue from what we had done in the last discussion. So we are going to now talk about the construction of the maximum likelihood method. So we are motivated in the earlier video, and now we are going to talk about the actual stuff. So let us see how to do it. So what we do here is that we take a random sample x1, x2, xn from a population, and the population is, as you know, given by a PDF. In our case PDF, PMF you can write down yourself. You have a PDF, and from that PDF this random sample has an observation small x1, small x2, small xn. Now you want to ask yourself the question, suppose I take epsilon very small, what is the probability that all the observations of the random sample, or of the random sample if I take, so the random sample would lie within this, would lie, what is the probability that these, what should be the value of my parameter theta? So the probability that x1 lies between x1 minus epsilon to x1 plus epsilon within a range around x1. So you want what is the probability distribution? What should be the value of theta so that x1 equal to small x1, x2 equal to small x2, xn equal to small xn. This set of observation has a high probability of occurrence, but you know the probability of occurrence of this exact observation is 0 when you have a PDF. What you can say that I want the observations of x1, x2, xn, all these things to be within a small neighborhood of these these observations that I want, x1, x2, xn. So I want that capital X1, the observation, should lie between x1 minus epsilon to x1 plus epsilon. That is in a epsilon neighborhood of small x1, and x2 in a epsilon neighborhood of small x2, and so forth. So what should be that probability? Now, when will that probability be maximum? That's exactly what the story is about. So here we start discussing the story. So here we are talking about the probabilities. So probabilities of x1 lying between x1 minus epsilon to x1 plus epsilon xn lying between xn plus epsilon to xn minus epsilon, because these are independent, can be written as product of probabilities. And because you know how to compute the probabilities of each of the xi's, you can compute it like this. Now if you take epsilon very small, very small, because this is a continuous curve, the fx, the density curve is continuous, I assume that when epsilon is very small, the change in the function value is not appreciable. It's not a huge drop or something like that, a very minute change which I ignore for the moment and keep that fxi theta, that particular value at xi, the density value, assume that in that very small range the value hardly differs. So this integral can be approximately written as 2 epsilon into this, because then if I keep this as fixed, the fx value as fixed, and that goes out of the integral, and remaining d theta is theta, and then you put xi plus epsilon, xi minus epsilon, the xi is cut off, and so you have 2 epsilon. You might ask me, okay, so here is your point. You have started, this is tomfoolery. How do you know it will remain constant? No, it will not remain constant. It will remain constant if it is a uniform distribution, of course. But in general, it will not remain constant. But if you take the epsilon very small, that function value would differ very little over that interval, because the epsilon is very small, however small you can imagine, no matter how small. So then we can do some hand waving. As Sanjay Mahajan in his very fantastic books Street Fighting Mathematics essentially gives us the feeling that too much rigor might not be always healthy in getting through ideas. And in one of his TED Talks on this aspect, he says rigor causes rigor mortis. So sometimes you can actually get away by arguing like this and get into the heart of the idea. So it is not an argument that you are doing as a mathematician, it's more like a physicist doing an argument. But sometimes in mathematics it is good to think like a physicist. Okay. Now what happens is that once you do it, once you calculate each of these intervals like this, so for every I you have the same story. So then you know how to write down the probability. The product of all the distributions, product of the individual distributions which are the same basically, into 2 epsilon to the power n. So you see 2 epsilon to the power n does not have theta. So the probability value, the value of theta for which this probability value is maximum, will be obtained by maximizing this product of density functions. Product of the individual density functions of each of the random variables x1, x2, xn of the random sample. And this product of this density function is also known as the likelihood function, because this is the function whose maximum value you seek, you seek a theta whose value would be maximized by that choice of that particular theta. Okay, so that's the key idea. So you would now know why we talk about a likelihood function. So immediately by doing that little trick, we get into the heart of the matter, and that's the key idea, that you can very fast get into the heart of the matter. What happened, let me tell you, that actually I do not know. When I was actually doing the other part, my video suddenly got stopped. I have no clue why it did, because I have short videos much longer than 20 minutes. I was thinking of finishing in 5-10 minutes. But whatever it is, I can still go on, or maybe I've clicked somewhere wrongly. So there will be 2 videos now, one after the other. So you should forgive me for this, right? And take it. Let me come back to what's likelihood method. So I have already told you what a likelihood function is. I don't need to define. And our whole idea is to maximize the likelihood function with respect to theta belonging to some range. Like if for example you have exponential distribution, your lambda parameter has to be strictly bigger than 0. That kind of thing, because if you have normal distribution, your mu or sigma square is always non-negative. Mu does not need to be non-negative, it can be anything, that kind of thing. So there has to be a range, right? So this is the idea. So when you find that theta hat which maximizes the likelihood function, and that theta hat must be a function of x1, x2, xn, the choice, the observation. So in general, theta hat can be viewed as the function, I can write it in terms of the function of a random variables, capital X1, capital X2, capital Xn. So it depends on what observation you are seeking of the random variables. You change the observation, the theta hat function would change. So this theta hat, the value of this statistic now will change depending on the choice small x1, small x2, small xn. Because the theta hat here, the minimizer, assuming a minimizer exists, would depend on x1, x2, xn, because ultimately the likelihood function also depends on x1, x2, xn. Though we are not writing L x theta every time, but we tacitly assume that theta is always there. X is always there. Observation x1, x2, xn is always there. If you have more than one parameter, vector parameter, you can just do the same thing. So instead of one theta hat estimation, we'll have more than one estimation, which is example for a normal distribution, which you have in your notes. Again, So these are in your notes. I would request you to look at it. Sometimes it is clear that if you take the log of the likelihood function and then take the derivative and minimize, or partial derivative and minimize with partial derivative with respect to theta, that's much more easier to compute. Because once you have we have some exponential powers, like in many of these distributions, like E always appears. Like if you go to say gamma or exponential, normal, it doesn't matter. Suddenly this log likelihood becomes much more easier. But some cases likelihood is easier. For example, if you take a uniform distribution, I would tell you to go with the likelihood method, just the likelihood function, not the log likelihood. So when you have an exponential term in your PDF, log likelihood is better, because then you can forget the exponential, you can just write it down. So it is possible because log is an increasing function, because if theta hat is the maximizer, then L theta hat is bigger than equal to L theta for all theta in that chosen set. So you can apply the log epsilon, log base E, that is natural logarithm on both sides, because log and natural is an increasing function, and you will get this equation. So instead of just taking a partial derivative with respect to L theta, del L del theta, I take del theta of log base E of Lx theta, and that evaluated at theta equal to theta hat must be 0 if theta hat is the solution. So basically, first when you take the derivative and find out the solution, you might ask, okay, what about the second order derivative? Actually, in most cases you don't have to find the second order derivative, because the likelihood function turns out to be, or log likelihood function immediately turns out to be a concave function, for which a critical point, that is the derivative or the gradient vanishing, the point where derivative or gradient vanishes, that point, a critical point, is always a global maximizer. That has been written in the notes, but I don't want to disturb you on that. That is why in the notes you will observe a second order conditions have also been written down. Second order conditions had also been written down there. So this is something to observe very carefully, that I have written down the concavity part. I have also written down the second order conditions, so that you are not confused. If you don't want to bother about concavity, don't bother, but you can bother about second order conditions that you know from your calculus courses. So here is an example with which we will end our talk. Here is an example. So here you are drawing a random, is one of the examples in the notes. You are drawing a random sample from an exponential distribution. So you construct the likelihood function and then take the log of the likelihood function. Then take the del theta of the log likelihood, and then theta hat is given by 1 by x bar, which was also the theta hat you obtained by the method of moments. So here is one guarantee that this method is working, because it is also matching with another method which you already know. And of course in this case, though the function is concave, but still I will do a second order check with you. The second order check, when you take the second order derivative of the log likelihood function at theta hat equal to 1 by x bar, you get minus n x bar square, which is always a strictly negative number. So when the second derivative of a function is strictly negative, of a single valued function, single variable function is strictly negative, when a second derivative of a single variable function is strictly negative at a critical point, that is at the point where the derivative vanishes, then you know that such a point is a strict maximizer. So this theta hat is a strict maximizer of the log likelihood function, and hence of the likelihood function. So this is a maximum likelihood estimator. Thank you very much. If there are questions, you can send me your ideas. If you want me to have a different kind of presentation, that is also fine, but I have at this moment no idea of how I am just gonna do it. So maybe your help would be much appreciated. So thank you for being with me here. Though I won't see you, you can still see me even virtually. Maybe you would not like to see me at all. That might be a good at all, because who does a course? Every student has the same feeling. I too was a student, so there is I being a faculty now doesn't mean that my heart as a student doesn't reach you. but stay well, stay safe, be fine. This too shall pass. Basically, I'm taking this word phrase from my best friend, who keeps on telling that this too shall pass, this too shall pass. And I hope the day will come when we will see each other, if not in the classroom, at least in the shopping center or somewhere in the campus. Thank you very much.